Jeff will pinpoint that in the TDM. I hope that that gets published. He's a little worried about being. Anyway, that's another story. Someone will do the TDM, we'll get that nailed, the exact diameter. And of course the aluminum in these plates, very curious plates that are about 40 nanometers thick. Here is an EDS map that was done by Jeff. And this shows, again, this is a nice SEM image, the electron microscope image, because you can see a lot of these little grains that are rich in iron. We know that because here's the iron. So look at this cluster, let's see, right here, and there's your iron. You see, these are rich in iron. And we have these other elements too. This is before separation, and it's a little tricky separating out. I'll let you, this in the paper so you can study it. But it does look like they're intimately mixed. The iron and aluminum is what I'm getting at here. The oxygen associates with carbon and with silicon and with iron, and so it's a little hard to figure out where the oxygen resides from this map before NEK soaking. I don't actually have that in the talk now. I wish I had all this data I could show you in a short time. Thank you for your patience. We're now 15 minutes into it, but you're not ready to go yet because we don't know where the silicon and the carbon, where are those coming from? Okay, read on. This is a little different topic, but here we go. The sol gel process, this is the Livermore report, is very amenable to dip, spin, and spray coating technologies to coat surfaces. Dip coat various substrates to make sol gel, iron oxide, aluminum, Viton. Aha, carbon, organic. There's your carbon coming in. Why do they add Viton? We'll see. But anyway, there you see the carbon coming in. The energetic coating dries to give a nice adherent film. Gosh, that sounds like just what we've got, a nice adherent film. A paint, but an explosive paint. This is not like ordinary paint, folks. This stuff is, I will show you, very highly energetic. A little more from the gas report, April 2000, Livermore Laboratory. The nature of wet nanocomposites affords an additional degree of safety. The wet pyrotechnic nanocomposites cannot be ignited until the drying process is complete. This property should allow the production of a large quantity of the pyrotechnics that can be stored safely for some time and dried shortly before its use. Why? You could have somebody go in and paint this on. He would just think it's ordinary paint, probably rather thick, and it would be quite safe until it dried. Then it's very dangerous. Okay. Okay, now silicon. Here's a 2004 report where we learn about how this silicon works. That doesn't mean they hadn't been studying it before, but this is where they discuss it that I found. I didn't try to find the earliest, but here they're talking about. By introducing a fuel metal such as aluminum into the metal oxide silicon oxide matrix, energetic materials based on thermite reactions can be fabricated. There's your silicon part of the matrix to hold these things. Organic additives can be, okay, what's that for? This is carbon. Those of you who know a little chemistry, the organic refers to a carbon presence. Organic additives can cause the generation of gas upon ignition of the materials, therefore resulting in a composite material that can perform pressure volume work, like explosion, cutting action. That's the sort of thing that you can get by adding an organic, because you generate gas. See? Expansion, rapid and destructive if you design it that way. Here we go. We're going to talk then about a method of making nanostructured energetic materials, specifically explosives, propellants, and pyrotechnics. Notice they include explosives in that list. And this is in the public domain. Since I read a little more about this, sol gel method allows for the addition of insoluble materials, for example, metals or polymers, again, carbon bearing, polymers to the viscous sole just before gelation to produce a uniformly distributed and energetic nanocomposite upon gelation. So you have then these thin films possible, thin films of the hybrid inorganic, organic, energetic nanocomposite. Hence, aluminum, iron oxide, carbon, and silicon part of the matrix. Where did we go? What is happening? Okay, I don't know. There is one. Can you see what's happening? Because maybe it was. Well, it is published, and so you can read about it. It's just a little bit glitched here. I don't know what the computer shows it just fine. I could show you that, but. Well, again, the organic is to prevent gas generation, so you get this explosive force.
Phyton's like the super best whole range material.
Oh, I don't know why they chose that particular organic. Yeah. In general, they talk about polymers that give this effect. Gosh, I'd like to show you some more data. You have a question?
Yes. If we're talking about paint, I'm not a scientist.
Explosive paint.
If we're talking about a kind of paint, would there be
Well,
anywhere near enough?
you can paint it on. Oh, enough. That's a good question. I'm actually getting to that. Because there's tons in the dust. Let me give you that argument while we're... Sorry, you're going. I can't get this to show you. I can tell you, but, you know, I'll tell you. In the paper, we discuss the amount of this red-gray material, the chips that we found, which we weighed. Jeff weighed it, actually, a very sensitive scale then. To give you the quantities in a quantity of dust. The percentage was about, oh, you're back. Wonderful. Ah, thank you. Good job. Okay, so let's go. I'll come back then to the argument of how much there is. But it boils down to, I estimate, right around 9 tons of the unexploded material in the dust. Now, why did I say this stuff is, it behaves like an explosive? Okay, what Jeff did is he ran the chips in a differential scanning calorimeter. I suggested it. Jeff did the work. You know, it's a great team. But the fact is, Jeff said, you know, Steve, if you tell them you want to run material from the World Trade Center in a DSC, you know, at the university, no, they're not going to let you do it. So he did it. Bless his heart. And here's what we see. We have to know how it behaves when it ignites. Okay, that's it. That's really important. And I showed you already the result that you get these iron-rich spheres produced. That implies a very high temperature. All right, so we already have data that there's a high chemical reaction. Now, how did Jeff ignite these? He heated the material slowly. This is temperature and centigrade to 700 degrees centigrade to stop. Now, iron melts at 18. See, help me on this. Is 15 or
17? No, 1535.
1535, right. Centigrade. So it's well below the melting point. This is not how you melt iron. It's not anywhere near hot enough. But, in fact, it would be damaging to the instrument if you heat it to that high, 1535, I should think. But there's a peak here at right about 430 centigrade. And we did this 4 times, as reported in the paper. And each time, the ignition point is close to this temperature. Now, the red curve, this is interesting. This is known nanothermite, published by